Hello, this is Math 280 Multivariable Calculus. I'm Professor Wheatley. Our topic today will be limits and continuity in higher dimensions. For the most part, limits of multivariable functions are very similar to limits of single variable functions, but there is a slight difference, though really that difference is, it's not cosmetic, but in a sense it almost is. So a few examples first. Limits work basically the same way as they did before. For the most part, things that are continuous on their, or sort of basic functions are continuous on their domain. So, I mean, this function is nothing particularly unusual about it. We can see it's got some problems with its domain in the denominator. We can't plug in things that sum to 7. Other than that, everything else seems to be pretty clear, and it is. And so in a case like this, if you can plug in, do it. There are always counterexamples out there that sort of cause a certain amount of grief. But for the most part, if you can plug into things, just like in single variable calculus, usually it's okay to do so. In case of a piecewise function, maybe there's always some questions there. But this is certainly 3/7, and you can see if you were to make a graph of that function, this thing would approach 3/7 as you approach 0, 0. Everything is fine with that. Same thing holds true for functions of more than 2 variables. I don't care how many variables you have down here. For the most part, if you have functions that seem like they can be plugged in and there's not some question about it, plug it in. In other words, I mean, this is absolutely the natural log of 2. Right, so no problem plugging 1, 1, 1 in there. ln of 2, what you get, no issue. All the usual algebraic rules apply. Limit of a sum is the sum of the limits. Limit of a difference is difference of the limits. Multiplying by a constant out front, perfectly fine to do that. Limit of a product or quotient is the product or quotient of a limit, provided that the denominator is not 0. All that good stuff, exponentials and roots, everything that you spent some time on in Calc 1 still holds true for higher dimensions. There's no issues there. Okay, so here's an example of one that we have to do a little bit of work on. A lot of the same tricks even to deal with things come into play for limits of higher dimensions. So here we can't just plug in, right? Here we can't just plug in, because if we plug in, we get 0. But we see that as long as, well, let me say this over here. We see that regardless of this, this function can be factored. X squared minus y squared over x minus y equals x plus y, x minus y over x minus y. This is x plus y as long as x minus y is not 0, right? And that is to say, i.e., as long as x is not equal to y. Well, remember, the thing that limits don't care about is the point in question, right? In other words, the limit doesn't care what's happening at 1, 1, only what's happening as you get closer and closer to it, right? So as long as x is not y, this expression here simplifies to x plus y. And we don't care about this point. We care about points getting closer and closer to it. So the limit as xy goes to 1, 1 of this guy is equal to the limit as xy goes to 1, 1 of x plus y. That's fine. Just plug in 2, right? And if you recall, in Calc 1, we had this notion that if 2 functions were equal except possibly at a point, then their limits as you went to that point were equal, right? Same idea holds true here. If 2 functions are equal except possibly at a point, or really in this case it could be at more than one point, but this is the only point in question, then their limits are going to be equal also. So we can note here that 1, 1 is not in the domain of the function x squared minus y squared over x minus y. But it's not the only bad point. This entire line is not in the domain, right? So the entire line y equals x, not in the domain. The entire line is not in the domain. And so if we asked about the limit as x, y went to 2, 2, we would have exactly the same trick to play, right? And so what is, I want to say this, well, okay, we could say it now. It's worth it talking about it. When you approach 1, 1, the difference is in single variable, you can approach it from the left or the right, more or less. Other ways, 2 from the left or right. But here, there are lots of ways to get to 1, 1 in the plane. One way that you can't get there, though, is you can't get there along this line. This line is not in the domain, period. The whole line is excluded. So if I approach 1, 1, I can never approach it along this line anyway. This is the only trouble line. This will make more sense in about 5 minutes, but this is a trouble line here. Okay, let's do another one here, very similar. So again, this idea of factoring, we did that a lot in Calc 1 with limits. It comes into play here too. What about something else? Conjugate pairs came into play a lot in messing around with limits in Calc 1. They are, again, a useful notion in multivariable. Limit xy goes to 2, 2. The function x plus y minus 4 over square root x plus y minus 2. Here we see a number of things. First of all, this quantity cannot be negative, otherwise we have the whole thing fall apart. So this x plus y less than 0, this half plane, this is not in the domain, not in the domain of this function. But neither is the line x plus y equals 4. Why? Because if x plus y is 4, we have root 4 minus 2. That's 2 minus 2, that's 0. So neither is the line x plus y equals 4. Right? So maybe you draw the picture here. X plus y is less than 0, right? We can cut a half plane. Y equals x is okay. That's a good part of the domain. And everybody over here is a good part of the domain too. So everything I'm shading in orange is part of the domain, but there's also this other line. Cut it. So orange is good, black no good, and then the line x plus y equals 4 is also cut out of the domain. So the domain is all this orange stuff. Delete this dashed line. So the domain is everything over here, including this orange line, but not this black dashed line. That is not part of the domain. So how do we handle this guy? We see this function, if we use conjugate pairs here, right? The conjugate pair of this, square root x plus y plus 2. In the top, something nice does not really happen. You get some junk, which I will not attempt to factor. In the bottom, the roots cancel, which is good, so the roots are gone. We're left with just x plus y minus 4. And take a notice that as long these can cancel if x plus y is not 4. Lo and behold, x plus y cannot be 4. X plus y cannot be 4. This is not in the domain. Cannot approach the point 2, 2 along that line. So this is equal to square root x plus y plus 2. So therefore, again, you use this notion that the point 2, 2 doesn't matter what happens there. What matters is what happens around it. So you have this equal to the limit xy goes to 2, 2. Get rid of this of square root x plus y. Oopsies. X plus y. Excuse me. Plus 2. So, and now I can just plug in, right? So you plug in here, get 4. And there you go. So again, the 0.22 is on this black dashed line. You can't even approach it along that line. Right, so there's a couple of examples of how limits algebraically are very similar to limits in Calc 1. All right, here goes a discussion about limits not existing. In Calc 1, one way for a limit not to exist is when the left and right hand limits weren't equal. It was worse than that, though. It was if you approached a point 2 different ways and you got 2 different limits, you couldn't possibly have a limit there. Now, 2 different ways meant sort of maybe you went on, sometimes, you know, think about a function, maybe you went on an entirely rational path versus an irrational path, if you recall. Maybe the Dirichlet function is an example of that. But here, that idea of 2 different paths is much, I think, easier to see. So, limit must be the same along all approach paths for a limit to exist. Limit must be the same along all approach paths for a limit to exist. So, example. Here is a function which is piecewise 2xy over x squared y squared when xy is not 0, 0. And let's call it 0 when xy is 0, 0. Right? I'd like to show f has no limit at, oopsies, not x equals 0, xy equals 0, 0. In other words, this is certainly defined at 0, 0. I'd like to show it does not have a limit there. Okay, let's draw the picture first. Here is the xy plane. There's 0, 0. I can approach 0, 0 any way that I feel like. In particular, I can approach it along lines. So I can come at it like that, along the line y equals x. I can come at it like that, along the line y equals negative x. I can come at it along the line y equals 2x, or the parabola y equals x squared. It doesn't make a difference. Turns out lines are good enough here. But, so let's take a line, I don't know why I'm saying straight, a straight line through 0, 0. Right? It has equation y equals mx. Right? M is a constant. M constant. Along this line, what does this function become? Right? Y equals mx means f of xy becomes f of x mx, right? Therefore, the one point I don't care about here is 0, 0. I'm always in this part of things. So that means f of xy becomes 2x mx over 2, x squared plus m squared x squared. Okay? So that's 2mx squared over x squared times 1 plus m squared. All right? And this is true at along any line approaching 0, 0, but not at 0, 0. That doesn't matter for the limit. Right? I can cancel these out as long as x is not 0. Right? So I can cancel these out, and I will get 2m over 1 plus m squared. This is true when xy is not 0, 0. Because think about it. If x is 0 and you're on this line, that means y is 0, right? So if x is 0 and you're on this line, that means y is 0. So for any point that's not 0, 0, this is what the function boils down to along one of these lines here. Okay? So this depends on the value of m. Look, it's constant. M is changing as a constant, so if I change m, this will change. But there's no x's and y's there anymore. So the limit as xy goes to 0, 0 of f of xy is equivalent to the limit xy goes to 0, 0 of this function 2m over 1 plus m squared. Well, there are no x's and y's in there. Just a constant, right? Limit of a constant function is a constant. So this is equal to 2m over 1 plus m squared, dependent on the value of m, right? Each line approaching gives a different value, right? Here's y equals x. I approach along this line, right? I approach along y equals x, right? Along y equals x, the limit, m here is 1, so this is 2 over 2, which is 1, right? If I approach along this line, which is y equals minus x, we have negative 1, right? This is negative 1, right? The limit is minus 1, right? And so it turns out, too, that if the steeper these lines get, take a look. I mean, if I had the line y equals, say, 10x, this all of a sudden becomes 20 over 101. That's about a fifth. If I had y equals 1,000x, right? This is 2,000 over 1,000,001. That's really small. These limits are getting smaller and smaller and smaller, right? So what's going to happen is there's going to be some jump. There's going to be some jump there. It's never going to be something smooth. There's a jump from these limiting values down to this 0, 0. In other words, if I approach along this line, it looks like the function's going to the value 1, but then it suddenly drops down to 0, 0. The steeper these lines get, the less severe the drop is, but still it's a drop. This is just a pretty severe drop here. That's a pretty severe drop. And so there is a discontinuity in this function. There's a drop there. So so there is there's a jump. There's a discontinuity. So a jump from these limits to f of 0, 0, which is 0. Therefore, there is a discontinuity at 0, 0. Right? Kind of like this, how do I say this here? Like a funnel almost there. If you look at the graph, you'll see what I'm talking about. All right, back to continuity. So that's a good point to bring us up here. Continuity is what we want to talk about next. Continuity, the same ideas apply for limits or for functions of more than one variable. Continuity implies that there are no jumps or gaps intuitively. So definition, f of xy is continuous at x0, y0 if the following things hold. First of all, the function must be defined there to even be continuous, to even have a chance to be continuous. That is necessary but not sufficient condition for continuity. F is defined, and the limit as xy goes to 0, or lots and lots of botching here. So y goes to x0, y0 is f of x0, y0. Right? In other words, the function is defined at a certain point, and the limit as you approach that point should be the functional value. Right? This is the same definition we had for a single variable function. Okay. Another no limit problem here. Another no limit problem. Let's take a look at this one. F of x, y is x to the fourth over x to the fourth plus y squared. I'd like to show this has got no limit at 0, 0. Please don't think that 0, 0 is some sort of a bad point. It happens to be the examples are sort of made to work like this, but there are lots and lots of other points that functions can have no limit at. It happens to be that these examples are straightforward and they happen to work with 0, 0. Okay, how about y equals mx? Lines y equals mx. In the case of lines, what does the function become? Yeah? The function becomes x to the fourth over x to the fourth plus m squared x squared, which is x to the fourth over x squared plus m squared. And cancel out two of those guys, and we're left with x squared over x squared plus m squared, again exactly when xy is not 0, 0. Okay. So here we're just plugging in mx for y, right? So this is what happens when we do that. But that means that the limit xy goes to 0, 0 of f of xy is equal to the limit xy goes to 0, 0 x squared over x squared plus m squared. I can plug in 0 here, right? The top is 0. The bottom is 0 plus something, which is going to be 0. And this is true for all m not equal to 0. All m not equal to 0. Now, m equals 0, we have a little bit of fuzziness going on because we have 0 over 0, right? That's one of those indeterminate forms. But for all m not 0, the limit's actually 0 here, right? So far, this has not been that helpful, actually, in getting us to show we have no limit, because we have a limit at every single m besides 0, and m equals 0, things are a little bit hazy still. Okay, let's try again here. Yeah, okay, let's go ahead and leave that for now. We'll come back to that in a minute. Let's try parabolas now. So lines didn't really quite work. Let's try approaching along parabolas. Y equals kx squared, right? Here, let's take a look. Along this parabola, when you're kx squared, x to the fourth over x to the fourth plus k squared x to the fourth, which is x to the fourth over x to the fourth 1 plus k squared, which is 1 over 1 plus k squared. Again, for xy not equal to 0, 0. Now here's a guy like before. Here's a guy that's dependent only on k, right? So here's somebody that's dependent only on k. So therefore, along these parabolas, the limit xy goes to 0, 0 of f of xy is equal to 1 over 1 plus k squared. So for example, if k equals 1, the limit is 1/2. If k equals 0, then the limit is 1. Limit is 1. So the parabolas turn out to be more useful, actually, because you could see that when I squared an already squared term, I could pull out all the x's. I could get rid of every x and y. I just had this constant term in there. And actually, what's incidental to this is that when k equals 0, this is the equation y equals 0, which is the same equation when m is 0, right? But if y equals 0 and x is not 0. This is just 1 anyway, right? So in fact, y equals 0, the limit is 1. That's exactly what this is saying down here. So if we'd recognized that, we could have done up here. We could have said, OK, the limit is 0 for m not 0. The limit is 1 for m equals 0. Again, when you're on the line with 0 slope, you're on the line y equals 0, but you're not at x equals 0. You're at points difference, so this is going to be just 1 all the time anyway. But still, this is not sort of typical. The better take-home message from this example is if lines don't really do the job for you, try something else. Try parabolas. Try some other way to approach the point that may be helpful. So the limit doesn't exist, right? And certainly, this function is discontinuous at the point 0, 0. Not only for that reason, but it's not even defined there. F is a discontinuous at 0, 0. It's not even defined there. F not even defined at 0, 0. And that's discontinuous. And so was the previous example, too. Neither one of these is actually removable. Neither one of these is a whole. So there's no way we can define this function at 0, 0 to make it continuous. It's not possible. Same with their other functions. Remember in Calc 1, you had discontinuities that were wholes. You could just define a function to be a point there, define it to be the limit, make it continuous. Can't do that here with this one. OK, one last question on continuity here. We can talk about continuity of a function. Again, the same kind of rules apply. Most functions are continuous on their domain. This is true for functions of multiple variables as well. So let's talk about the function sine of y over cosine x. This is continuous where? Right, so sine of y over cosine x, where is that guy continuous? OK, it is continuous on its domain. Continuous on its domain. What is its domain? When cosine x is not 0. Cosine x not equal to 0. This means x is not equal to pi over 2 plus pi n, an integer, right? Remember, these are all the odd multiples of pi over 2, right? Pi over 2 plus pi is 3 pi over 2. Pi over 2 plus 2 pi is 5 pi over 2. Pi over 2 minus pi is minus pi over 2. So as a consequence, f is continuous almost at every point except for these issues. Continuous on all of R2 except for points x comma y, where x is pi over 2 plus pi n, an integer. So it's R2, delete these points. Notice the y values in these points are allowed to remain free. So these are vertical lines, right? So how do I draw the domain? The domain is everybody in R2 except for dashed lines at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and then so on and so forth. So in other words, every pi, there's another dashed line. So the domain here is strips, strips that are open on both ends and are a length pi. OK, that's it.